summing up, there have been a lot of deterministic games. We have spent some of the today's lecture on chess. Some of the ideas are also valid in many other games. Checkers, for example, is one such game where in 1994 machines defeated human champion, right. Chinook is the machine software, it defeated the 40-year reign of humans by defeating a world champion in 94. It used a pre-computed endgame database and it evaluated a total of 444 billion positions. We consider checkers as now solved. Similarly, in chess, Deep Blue defeated Garry Kasparov in 97. It uses a combination of opening game, end game, mini-max in the middle game, and undisclosed method for doing extending some lines of search using quiescent search and many different kinds of search. Sometimes it will go up to 40 depth. Typically, it will go to 12 to 14 depth, but some cases it will go to 40. That is a lot of depth, and because of that, it completely stumped Garry Kasparov at the time. Later chess softwares have become so good that no human wants to play chess with the machine. The best players, by the way, are neither humans nor machines, they are a combination of humans and machines. So, the world hope is that in the limit of things, humans and machines will be working together. Othello, human champions do not compete against machines because machines are too good. Go was an oddity. It was an oddity because until 5 years ago, humans will not play against machines because machines were too bad. I have been teaching the AI course for the last 5, 6, 7 years, and earlier I used to say there is no hope that machine is going to defeat humans in Go for a very long time. Why is that? This is because if you compare chess and Go, chess is 8x8 board, Go is 19x19 board. Forget universe playing it, it is just too big. In chess, typically your game finishes in 100 moves, in Go it takes about 300 moves. The average branching factor in chess is 35, the average branching factor in Go is 235. If you really played this move, you will not be able to search beyond 3 or 4 depth typically. And there are many other additional complexities, there are some people may start with some advantage in the beginning, etc., etc. Players can even pass, say I will not play this game part, you play the next game again, next turn again. So, in the game of Go, humans were so good and machines were so bad that they will not compete. And suddenly, and I would say suddenly because by 2015 we had no idea, and in 2016 this had already happened. DeepMind's AlphaGo defeated Lee Sedol to end the human reign. Lee Sedol is considered to be the Federer of Go. Go is a more oriental game, so Chinese, Japanese, Korean players are the best players. I think Lee Sedol was Korean. And it used a combination of deep neural networks and tree search, but not of the minimax variety, sampling with tree search. So, instead of going through the full subtree, I will just sample a part of the subtree, I will sample a part of the subtree and I will do it intelligently, and I will do it again and again and again, and that is called Monte Carlo with tree search. Monte Carlo is the sampling idea in the context of tree search. And typically I teach both of these, but in this class I may end up teaching only one because of limited time. Now, of course, there are many other games. So, some games are deterministic and perfect information like chess. In chess, I do not know anything more than my opponent, right, and everything has deterministic outcome. Then there are games of chance, but everybody knows everything like Monopoly. I am not saying it is an interesting game or it may or may not be, but Monopoly you roll a die. When you roll a die there is chance, but everybody knows how much money you have, where your establishments are on the board, etc., etc. Then there are games of imperfect information, but deterministic, right. For example, everybody knows, not everybody knows everything, but the game proceeds deterministically. Then there are games of chance, right, but with imperfect information like poker. In poker, you have some cards, the other person has some cards, you know yours, the other person knows theirs, nobody knows everything. But there is chance because new card may come out any which way, right. Similarly for bridge, initial board positions you do not know, may come out randomly. So, there are different kinds of games. So, very quickly what happens if I have a game of chance? You know, life is not very different if I have a game of chance. So, if I have a game of chance, what I need to do is that not only do I have a min and a max, I have a chance in the middle, like I have rolled a die and I have 6 different things that can happen. And so, if you think about it, you will have a max node, you will have a min node, but you will also have a chance node which determine different things can happen with different probabilities. And in your control will be the max node, in opponent's control will be the min node, and in nature's control will be the chance node. So, now you are playing a game against your opponent, but you know that nature is coming into the middle. And what you do there is you do not do minimax because you can't, you have to figure out what to do with the chance node. So, let us look at an example quickly. And so, in this example, let us say we are here. So, if we are here in this node, what would the max node do? 3 or 5? 5, right? Here the max will do 5 and here the max will do 4. So far so good. But now above it is a chance node. This left subtree will happen with probability 0.4 and this right subtree will happen with probability 0.6. So, if I come to this node, what can I say? Well, I can't compute the best value because I should not compute the best value because it is not in my hand. I will not pick the left and get the best value. In fact, random event will happen, and so the best I can do is to take an expectation. And so, my expected value at this node will be 0.4 into 5 plus 0.6 into 4, and that is 4.4. Let us do one other. So, this would be 2, this would be 5, and this expectation here would be 0.4 into 2 plus 0.6 into 5, which is 3.8. Now, let us think about the min. So, the min says, min at this point, okay. So, the min says that I could go left and then random things would happen and the adversary will play, etc., and I will get 4.4. I could go right and then random things will happen and the adversary will play and I will get 3.8 in expectation. Which game should I play? Right, I should go right because I am a minimizer, so I will get a 3.8, and this sort of keeps going up. Basically, that is the only change with respect to the minimax algorithm. And this algorithm is called expecti-minimax. And it is a general principle. Suppose I remove the adversary, then it will become expecti-max. If I remove the chance, it will become minimax. And if I have all me, opponent and chance, then it will become expecti-minimax. I have already done this example. And its time complexity would be b to the m, n to the m, because let us say I have n chance nodes at every point, then my tree will have that much expansion. And then there are some imperfect information games, so we will skip this. So, here is where we are in a lot of the games. See, tic-tac-toe, we are not better than the best human, we always draw. Othello, we are good, better than humans. Scrabble, we beat humans. Backgammon, we beat humans in 92. Bridge, we are ranked among top players in the world, maybe we beat humans, I need to check. Poker was a hard game. Poker was considered a hard game, except in 2015, University of Alberta showed that at least the heads up limit hold'em poker is solved, and it was solved again by huge amount of computation, like months of cluster computation, large cluster computation, which led to playing poker as good as humans and defeating humans, right. In checkers in 94 it was solved, in chess in 97 we defeated humans, and in Go in 2017 we defeated the Go champion. 2016 we defeated the Roger Federer, but there was always Djokovic. So, that was J and from China I believe, and he was defeated in 2017 in Go. In fact, I asked myself this question before this class, is there any game which is now the Go of today? Like 5 years ago it was Go, right? Go was the next frontier, chess was solved, Go was too hard. Now that Go champion has been defeated, what's the next game? Dota. Okay, so Ishan says there is a game called Dota. It stands for? You don't know? It's a game, but he doesn't know the full form. And apparently that's the next frontier, maybe. I don't know about it. OpenAI is playing it, so maybe it's the next frontier. But at least I could not think of any. And so we will check out Dota just to get a sense of what it is. Maybe it is very hard. There are sort of these games which play in these very complicated video environments and so on and so forth, and you have to make a thing that kills people and moves around, and possibly that would be one of those. But this whole idea of board games which are sort of formal games which can be written in a formal specification and so on and so forth, I don't know what's the next frontier there. I think they are kind of solved. This leads us to the end of the lecture on games. Games have been fun to work on for AI researchers. AI researchers are really interested, they love games in general, people love games, and if you can play game for a living, that's a great life. They illustrate several important points about AI, how to do search in a large depth, how do you cut off search, what do you do at the time of cutoff, what different techniques can you use to extend search in a variable fashion, the idea of meta reasoning, how much to spend time here thinking and how much to spend time there thinking, etc., etc. It also exposes that perfection is unattainable, optimality is a luxury, we always have to approximate, and so let us approximate, but still get to a good solution and beat the next best thing that exists. That is an insight that we get from game playing, and game playing programs have traditionally shown the world what AI can do, and this is now changing, because now it is more about medical diagnosis, now it is more about using AI for this and the other, that and the other, but traditionally games have been one vehicle by which AI researchers have demonstrated the success in the field. Okay. So, we will stop here. Okay, thanks.